All right, so hopefully you got enough time to try this out. Let's just take a look. So you should be getting limit n approaches infinity. Let's just do the n. Actually, there's, the n plus first term is n plus 1 over x plus 2 to the n plus 1 over 3 to the n plus 1 plus 1, so that's plus 2. Nothing that's going to be distributing there over n x plus 2 to the n over 3 to the n plus 1. When we simplify that out, let's just put it all in a regular fraction, flip in the denominator as a multiple of the reciprocal fraction. We get n plus 1 on top, 3 to the n plus 1 on top, x plus 2 to the n plus 1 on top. Bottom, we get n, 3 to the n plus 2, x plus 2 to the n. Simplifying all that down, we get n plus 1 on top times, 3 is on the bottom. N plus 1 on top times 3n on the bottom, looks like, right? 1 left over, 3 down here, times a single x plus 2. When I take this limit, I'm not going to show every step on this one because we're just going over it. You're going to get, the limit's going to be taken, so I'm going to get x plus 2 over 3 at the end of the day. Looks all right? All right, so now when is this less than 1? That's when you need to converge. So x plus 2 is less than 3 for convergence, or negative 3 is less than x plus 2 is less than 3. Subtract 2 from both sides, you get the interval of convergence, which I mentioned is negative 5 to 1. Then you go back and plug these into here. What will happen if you do that, right? If I plugged in 1, you can clearly see I'm going to get n over 3 when everything cancels out, right? So, that's just going to diverge easily. The terms themselves are going to infinity, and the same thing's going to happen if you plug in negative 5. That n in the numerator is going to end up just taking things divergently. So both endpoints will diverge. Not going to show the work on that unless we need to, but that's the process there. So someone had a question on it. Just nth term test should be used on the two endpoints because the limit of those things are going to go to infinity, which clearly is not going to 0. So you can show by nth term tests that they diverge. Yeah, alternating series test will work for the second one. Well, for the negative 5, you can do alternating series test, and it will fail the first condition, right? For the other one, you're going to have to use nth term test because there's nothing alternating. So that leaves us to the back half of 10.7, which is actually the hard half of this, but it's also the less important part. So it's called representations of functions as power series. Now I'm going to give you two pieces of conflicting information here. This is the least important part of this section, but also this topic of representing functions as power series is the most important thing in the entire class. The reason it's not so important now is because starting on Monday, we're going to develop a systematic way in order to represent functions as power series. But right now, we're just going to kind of like mess around, like, oh, what if I took the derivative of this thing that I know? What if I took an integral of this thing that I know? Oh, yeah, not Monday, Tuesday. Sorry, Nicole. So we're going to kind of just like mess around with these things. In principle, that's not the way you're going to be doing them. You're going to be doing the systematic way that will start on Tuesday, not Monday. And that is an incredibly important thing, not only for our class, but also just for mathematics in general. The reason that it's so important is we're going to basically learn how your calculator in principle works or a computer works. Like, if you were to plug in something in your calculator, like sine of 3 or log of 3 or square root or something like that, how does it know what to do, right? At the end of the day, everything in computing has to come down to, ones and zeros, to binary, to very simple operations. There's no such thing in your computer that's just like, a log chip. It's not a binary operation. It's a very complicated function. So there's no necessarily easy way to just evaluate what sine is or log or any of these weird functions are at different spots. The way your calculator does it is it says, you know what? I'm going to approximate this function by an infinite polynomial that maybe looks like this. Infinite terms. And polynomials are very easy for calculators and computers to do because they're just multiplication and addition. That's a very simple thing. And you can number crunch that as much as you want. So it turns out that every possible function has a representation, which is called its Taylor series, which is a power series. And they converge somewhere and they diverge other places. We'll have to figure it out. But knowing these things is the secret to how all of this stuff is ever done on a computer or a calculator in the first place. So it's a tremendously important thing to understand how we can take these abstract functions and put them into just multiplication and addition of regular polynomials so that we can actually use them in real life. So that's the goal here. Today we're going to just kind of do this like end around way. And we're going to do it all based on one little fact that we know. But like I said, we'll do much better starting Tuesday. So imagine we've got a geometric series, a simple geometric series. Like summation n equals 0 to infinity of x to the n power. And this clearly looks like this. If I were to write out terms, I plugged in 0, I get x to the 0, which is 1, plus x squared, plus x cubed, And the interesting thing in this case is that I know the answer because it's geometric series. Most things we don't know the answer. So this converges if the absolute value of x is less than 1. That's like my r in this problem, right? Usually it's of the form a equals r to the n, so a in here is 1. R in this case would be the x unknown value. So as long as that x unknown value is between plus or minus 1, this thing converges. And what would it converge to? Well, the answer is a, which is 1, over 1 minus r, which is x. That's the answer. You get 1 over 1 minus x for this particular power series. So now you have a function which I know how to represent it as a polynomial. So if you were to write this out, for infinite terms, it is literally the same thing. It would be the exact same graph as this function over here. All right? Only on this range, but it would be the same thing. These two things are actually equivalent. This is not an approximation. Those two things are the same. Okay. So what we can do is just kind of play around with that and say, all right, let me make functions that are similar to this and kind of relate them back to a geometric series. That's what we're going to do. So suppose we're asked to find the power series representation of this function, which is going to be f of x equals 1 over 1 plus x squared. So somehow we have to get from here into this form over here. So let's see how we would do it. And once we figure out what changes we would have to make to get from here to the one thing we know, then we can figure out how to change it within the summation to get its power series representation. So the first thing we need to do, basically, is I need it to be a minus sign here, not a plus sign. So let's alter that. I get 1 over 1 minus. So what are we actually minusing in this problem? We'd basically be minusing an x squared. Right? Everyone see that this is the same as that? So here's the basic rule. What we did is if I looked back to this function over here, right, we replaced x by a negative x squared in the series. Right? If I were to plug in a 5, I get 1 over 1 minus 5. If I were to plug in a minus x squared, I get 1 over 1 plus x squared. So I can do that at the other side of this equality. I could say this is equal to the summation n equals 0 to infinity. Wherever there's an x, plug in a negative x squared. So I get negative x squared to the n. And then I can simplify this down and I get the answer. So I get summation n equals 0 to infinity. Let's bring out the negative 1 to the n. Negative 1 to the n. And then x would be power to a power is multiplied, so I get x to the 2n. And that's it. This power series representation is that function, 1 over 1 plus x squared. They're the same thing. So and it's a kind of an unusual concept. It's a totally new thing. Usually we're just doing straight algebraic stuff in math classes, but now we're actually thinking about infinite series and numerics and new stuff. So does anyone have any questions or just thoughts they want to chat about that type of thing? This is still section 10.7. It's in power series. Yeah, I basically just had to put it because I know that this series is this function. So if I make the new function look like the form of that function, see what I have to do to change it, I can do the same change within the series notation and get its associated series kit. What happened to this? Well, nothing happened to it. I'm basically trying to figure out how to relate these two sides of the equation, right? The summation equal to the function. So once I get this function, I'm saying, okay, I figured out something that looks like this up here. What's different about this to this? And I'm going to make the same difference on this side. The difference is for every x that there was here in this equation, now I put a negative x squared. So for every x there was in this equation, I put a negative x squared. Yeah, it's a little bit unusual, so feel free to ask any continued questions on clarifying it. Okay, so we do still have one more thing. I can't just directly say that this is exactly this because there's also the range on which it's true. So this was only true for x between negative 1 and 1. So I have to figure out, is there a range for which this works? So for that, we've got to go and do exactly what we did last class. So we're going to say B, find its radius of convergence and interval of convergence. So for which values of x are these two things the same? Right? And when does this thing here, the series, converge to this function? In other places, it will diverge and just be something completely unrelated to it. Okay, so we go through the usual thing, your ratio tests. So limit n approaches infinity of the nth plus first term, so that's negative 1 to the n plus 1, x to the, okay, what is the exponent going to be when I plug in the nth plus first term? A lot of people mess this up on the quiz. What power will be here when I simplify it? Okay, two good answers. 2 times n plus 1 in parentheses, that's what Arya said, and if you distribute that out, it becomes x to the 2n plus 2. Right, so you can see the whole progression there, but just be careful with the algebra. Perfect. So when I simplify this, the negatives are irrelevant. So I get limit n approaches infinity. There's 2 x's on top, so x squared. I actually don't even need the absolute value sign anymore because x squared can never be a negative, so I'll just leave it like that. And interestingly, there's no n's left in this either, so the limit is just x squared. And the question is, when is that less than 1? So you have to be a little bit careful with the squaring of this thing, but basically it's less than 1 on any range between negative 1 and 1. Right, so that means we have to go to the next step and plug in these two limits to see what happens at those spots. So x equals negative 1, x equals 1. If you recall, this summation was summation negative 1 to the n x to the 2n. Right, so if I plug in negative 1, these are actually kind of weird looking. If I plug in negative 1, I get summation n equals 0 to infinity of negative 1 to the n. I'm plugging in negative 1 here, so negative 1 to the 2n. But we said this last time, negative 1 to the 2n is actually just 1, right? Every single possible exponent here is going to be an even number because I'm multiplying by 2. Or I could look at it as like negative 1 squared to the n, which is 1 to the n, which is always 1. So this piece goes to 1. And I'm basically just left with plus minus 1, right? Just minus 1 to the n alternating. So if I looked at the limit as n approaches infinity of negative 1 to the n, it equals does not exist. Just goes plus minus 1 doesn't go anywhere, which does not equal to 0. So this diverges at the end of the term test. And if I looked at x equals to 1, I get negative 1 to the n, 1 to the 2n, which is actually just the same. If the 1 to the 2n doesn't go anywhere, so this diverges. So your interval of convergence is strictly between negative 1 and 1. And I guess I did say the radius of convergence too, right? So the radius of convergence is equal to 1. Center is 0. I could go 1 unit either direction from there. Any question with that? Oh, yeah.
Would we always have to prove what the interval of convergence is like this, or?
Well, if it asks for it, yeah. Maybe I'm not understanding your question, but
like the way we found it before we did all of this, from that step on, would we have to prove it like as we just did, or no?
For the most part, you're going to have to prove it like this. There's one possibility, because we are working off geometric, and we know the geometric starting interval of convergence. We can say this. We can say the geometric interval of convergence, right, is, in this case, x has to be negative 1 to 1, because x was my radius, r. And then I can do the same substitution we did in the series and say, all right, well, I'm plugging in negative x squared for x. So if I divide by a negative, that's not going to change anything. It does, actually. It changes both signs, but it changes both inequality signs, so we're basically the same. And if I took the square root of both sides, square root of a negative really is going to be a little bit annoying there. But in principle, right, that is going to be annoying. Yeah, I think you're going to have to go this way. But you can see that the basic idea is going to work, right? If I'm going to be between here with a negative x squared, any x value that's between negative 1 and 1 is going to satisfy this. So maybe I don't like this method as much. This is the more surefire way to go. All right, we're going to try another one. And then I go, maybe give you one to try out. Okay, so find the power series for 4 over x plus 2. I'm going to put, just for the interest of time, we're not going to be able to find this. I'm going to say find the interval of convergence at home for this problem. It's going to end up being negative 2 to 2. So you can check that out later if you want some more practice with basically what we did last time. Okay, so the new part is what we're going to do now. 4 over x plus 2. We have to turn that into something that looks like 1 over 1 minus x, right? And you can plug in something for the x. So how are we going to do that? Well, the first thing we can do, we need a 1 on top. So that's a pretty easy fix. We can basically factor this 4 out. So I'm going to say this is equal to now 4 times 1 over x plus 2. And actually, let's just flip the x so it's in the second position. So I'm going to just say it's 2 plus x. That's obviously the same thing. All right, so we got the first piece of information right there. Second thing that I need to match this up is I need a 1 down here. Then I need a negative sign. So we'll figure out all this stuff as we go along. So let's get the 1 here. How would I get a 1 in this leading position? And the answer is, well, I'd have to factor out a 2 from the bottom. So this is now equal to 4, 1 over 2, 1 plus x over 2. And this 2 can also be factored out. So it's going to look now like 4 over 2 is just 2 on the outside. 1 over 1 plus x over 2. So I'm getting there. We got the 2 1s. I do need a minus sign in the middle, so I'm going to do the same trick. I'll do a minus of a minus. Can we leave on the 4 on the top and just say 4 is equal to a? Well, see, the one fact we know, I guess you could, yeah. It doesn't really matter if you were to do that. We're going with 1 is equal to 1 minus x is equal to the summation of x to the n, right? And I'm saying, let's just have a 4 on the outside, And you're saying, well, why don't we just have a over 1 minus x, where this is equal to axn. It's going to be the same thing, as you can see. So yeah, that'll be the same. But I do like to, because we're always going to be trying to get in this section down to 1 over 1 minus x. I just try and get to the same basic form. So let's get the negative sign. So I get 2, 1 over 1 minus a negative x over 2. And we're actually good now. It's 1 over 1 minus something, so I could plug in this something for x, and basically multiply by a 2 on the outside, and then we've got it. So I know that 1 over 1 minus x is equal to the summation from 0 to infinity of x to the n. And let's make the two little alterations that we would need to get from 1 over 1 minus x to this thing over here. So 1 over 1 minus negative x over 2 with a 2 out front is the same thing as putting a 2 out front on the right-hand side of this equation. And wherever there was an x, plugging in negative x over 2. And now I have to simplify that a little bit, but essentially we've got it. So I have 2 summation negative 1 to the n, x to the n over 2 to the n. Generally, we break off all the little pieces themselves, because it'll be easier to combine things together. And we can actually multiply this 2 back in at this point. So if I have a single 2 on top and n 2's on the bottom, it's just going to cancel out one of those 2's on the bottom. So the final answer here is going to be summation n equals 0 to infinity, negative 1 to the n, x to the n over 2 n minus 1. And that's it. That is an infinite series, which represents that particular thing over there, 4 over x plus 2.
Professor, when you multiplied in the 2, why did it just make the exponent on the bottom n minus 1?
Okay. If I had 2 times 1 over 2 cubed, all right, something like that, what would be the result of this multiplication?
1 over 2 squared?
Yes. And if it 2 times 1 over 2 to the 33rd power, it would be, as a result, what?
1 over 2 to the 32?
Correct. So if it's 2 times 1 over 2 to the n, it's just 1 less power in the denominator, just like you've been doing with these two.
Okay, thanks.
No problem. Cole says, is the series equal to adding up all the values for 4 over x plus 2 to infinity? Oh, that's an interesting question. No. What it says is basically if I were to plug in x equals, say, well, it has to be in the radius of convergence. So let's say if I was to plug in x equals to 3/2 in this series and looked at all those infinite terms, the sum of that would be the same value as if I had plugged in x equals 3/2 up here. Right? So basically the functional value at different values of x, they're the same. So just imagine two graphs, right? 4 over x plus 2, I don't know, whatever it looks like. This thing, between negative 2 and 2, I don't know what it does before then, but between negative 2 and 2, it looks exactly the same as that function. So if I plugged in an x value here, it would give me the same value there. Does that make sense? That's a very good question. Note that this is not a series, right? This is just a function. This is the function also, but it's a function in the form of an infinite series. We'll see more about that in the coming days. Yeah, okay. I mean, if you generally have a general feel for it, but don't feel perfect, that's okay right now. We're going to see this a little bit more clearly starting on Tuesday. Okay. One more theorem, and that is this. Since a power series is basically just a sum of simple polynomial terms, so it's a sum of polynomial terms, we can do certain things to those terms without any problem. And specifically, we can integrate and differentiate term by term, as we know we are able to do with those two calculus operations. And the reason for this is because those two operations are what are called linear operators. That is, they work even term by term, and even if there's a coefficient, we can just bring that coefficient outside. So here's the three-part theorem, I guess. But if I look at the derivative of the summation n equals 0 to infinity of an x minus c to the n, that's the same thing as if I looked at the summation of the derivative of each term. It's kind of a subtle thing here, but this whole thing, right, this big summation is a function. I'm saying if I looked at that whole function as it is, as a single object, and took its derivative, it's the same as if I went in and took the derivative of each term, term by term, and then added up all those derivatives. And the reason for that is because it's just a power series, it's a polynomial. So basically it's saying something like this, right? If I were to take the derivative of a big function like this, which is a polynomial, it's the same as if I just said, well, I'll just take the derivative of term 1, plus I'll add to the derivative of term 2, plus I'll add to it the derivative of term 3, so on and so forth, right? Those are the same. That's what this theorem is saying. I can take the derivative term by term instead of just doing it at the end. And integrals behave exactly the same way. So that's the second part of the theorem, is I can integrate term by term as well. So ddx, integral, just did the back part. So the integral of the summation from n equals 0 to infinity of a sub n x minus c to the n dx is the same as the summation of all the baby little integrals term by term, because again, it's just polynomial terms. Summation of the integral of a sub n x minus c to the n dx. And the third and final part of this is something we're actually not going to prove because it's actually very difficult to prove. Turns out that when you do these operations, it turns out that the interval of convergence and the radius of convergence remains the exact same before and after integrating or differentiating. They're the same. So this leads to what I think actually confuses a lot of people. So we'll do 3 examples of it. And don't feel bad if this part seems a little backwards or confusing to you. So find a power series representation for y equals tan inverse of x. And by the way, just a quick thing. I did say this is kind of a confusing topic. If you'd never even understand this topic, it's not even going to be that big of a deal because, like I said, on Monday or Tuesday, we're going to start doing this in a more mechanical way. But I guess it's good to know for the homework. So, tan inverse of x. The only thing at this point that I know is the power series of this function, 1 over 1 minus x. So in what way can I connect those two things? Basically, it's the same thing we've been doing the first half of class, which is how do I connect this function to that function? You know, if I plugged in an x squared for an x, I can connect them, right? But now it's a little bit more complicated because the connection could be through differentiation or it could be through integration. So the connection is this. The integral of tan inverse, I think, is integration by parts, so that's not going to help. But the derivative of tan inverse is 1 over 1 plus x, and that looks like this. So the derivative of tan inverse of x is equal to 1 over 1 plus x squared. I think I might have said 1 over 1 plus x before, that's my bad. 1 over 1 plus x squared. And now I can connect this to this and then work backwards to tan inverse by figuring out, do I have to differentiate or integrate one side of the thing? So I don't know, we're going to cheat a little bit in this problem because we already did this. Recall that 1 over 1 plus x squared from 2 problems ago, we found it to be equal to summation n equals 0 to infinity, negative 1 to the n, x to the 2n. Now, normally you'd have to do those steps again from scratch, but here we can cheat and just build on what we knew or already proved today. Now, so I know this is equal to this, and I want to get tan inverse of x. So basically we have this, right? I know that d dx of tan inverse of x is equal to this summation. How would I get tan inverse of x alone? Well, the thing you'd have to do to both sides here is integrate away to get rid of this d dx on this side, and integrate on this side as well, and then you'd have tan inverse by itself. So tan inverse of x is equal to the integral of the summation of negative 1 to the nx to the 2n dx. But we just said by this theorem, I can just integrate term by term. So we'll bring the integral sign inside. So I get summation n equals 0 to infinity of the integral of negative 1 to the n x to the 2n dx. Now we have to integrate that thing. Actually, I have a question for you guys. Can you hear the periodic moans and groans by Luna over here? She really wants to go outside. I wonder if it comes across on video.
I haven't heard anything personally.
Oh, here's it.
You should let us see her.
Oh, she is whining. You'll definitely hear her moan when I pick her up. She wants out. Oh, she's fighting to stay in the window. Okay. What do you want? Out? Tell me what you want.
Oh, she's so cute.
I really kind of want to take a nap after this class, but I think I gotta take her out. See that?
What's up for you first, then you can take her out.
Okay. So where are we now? We have to integrate this thing. This is unusual looking, but it's actually very easy. Once you get past that, it looks different. How would I integrate anything easy like x squared, which is the power of x? It's just similar. You add 1 to the power, divide by the new power. Well, that's all this integral is. The negative 1 to the n is just a constant with respect to x. And I've got x to some power, so I just have to add 1 and integrate that way. So I get summation n equals 0 to infinity. Negative 1 to the n comes out. Power gets increased by 1, so 2n plus 1, divided by the new power, which is 2n plus 1. And technically when I integrate, right, there's a plus c. But basically we found it. I just have to figure out what that c would be. It's almost always, I think it actually is always going to be in this class 0. But we're going to have to do it anyway. Mike says he makes sure the cats stay in the video after he edits them. That's a good man, right? I should get on this group for me, I think. All right, so here's how we find the c. And all you have to do is just plug in the center point, basically. So plug in x equals 0 to find c. So what happens, because we've got tan inverse of x is equal to this function. So if I were to plug in 0 to both sides of this equation, and the reason I'm picking 0 is because the center and it knocks out every single term, basically. Tan inverse of 0 on this side is 0. And if I plugged in 0 on this side, every single term is just 0, 0, 0, 0. So this is just equal to the summation of 0 plus c. So there's nothing, c just equals 0. This is the answer. So it's kind of a creative, interesting way. Yeah, you should always just plug in the center to get c, because that's what. Otherwise, you're going to have infinite terms on the summation side. So you want to just cancel all those terms out so you can solve for what they need to be. But ultimately, this here is the end result. That's your summation. And the really interesting thing is implication of this. Let's plug in the numbers, right? So if I plug in 0, I get negative 1 to the 0, that's 1. X to the 1, x, over 0 plus 1 is 1. So the first term is x. Next term, if I plug in 1, is negative 1 to the 1, so that's minus. It's going to alternate. X to the 2 plus 1, so that's x cubed, over, the power is going to be the same as the denominator, so x cubed over 3. You can trust me, if you want to look at the next couple terms, it's like x to the 5th over 5 minus x to the 7th over 7, dot, 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 dot. So this infinite polynomial of that form, that literally is the same thing as tan inverse of x. It's the same function. Of course, this side is just kind of a conceptual thing. This side is a realistic thing that a machine or a computer can actually handle. That's kind of neat. And you'll see these interesting patterns emerge for all the different functions that you know. We'll be doing a lot of the main ones starting on Tuesday. Let's do another one. All right, another one is find the power series for f of x equals 1 over 1 minus x quantities squared. Well, how does that relate to the one thing that I know, which is 1 over 1 minus x? How would I get from here to there? And the answer is, if I took the derivative here, it would be similar to this. So I know that the derivative of 1 over 1 minus x is equal to, right, this is like 1 minus x to the negative 1 power, so it's like a negative 1 comes down out in front, over 1 minus x to the negative 2, or second in the denominator, times the derivative of the inside, which would be a negative 1, so this ends up being exactly 1 over 1 minus x squared. So the thing that I'm looking for, the derivative of the thing I know, is equal to the thing I'm looking for. So it's actually very similar to this problem we did over here. We'll just have to integrate both sides. So now on this side, that 1 over 1 minus x is equal to the summation of x to the n. So what we're saying is the derivative of the summation of x to the n has to equal 1 over 1 minus x squared. So now in this case, it's the opposite direction, but it's the same idea. Now I can take the derivative of each of these terms. So the derivative of x to the n, again, it's just power rule. It looks funny at first, but it's just x to a number. So I get the summation of n x to the n minus 1 equals 1 over 1 minus x squared. So there it is. That's it. That is the power series. I guess I should probably put in the limits here. So from n equals 0 to infinity of n x to the n minus 1. Right? That is the power series representation of that function. Which, if you were to write it out, let's write out a few terms of this. What does this thing look like in terms of the actual terms? Plug in 0, I just get 0. If I plug in 1, I get 1 times x to the 0, so that's 1. If I plug in 2, I get 2 times x to the 1. If I plug in 3, I get 3x squared, plus so on and so on and so forth. We would need to find radius of convergence and interval of convergence. Good question. Generally, yes, if they ask for it. If they don't, I think they just kind of care about you finding the function. Because finding the radius of convergence is kind of annoying, and trusting the endpoints is pretty annoying as well. So sometimes they'll just ask you for the function itself. But the complete answer does depend on the limits, right? This is not directly equal to this. It's only equal to this on the appropriate range where it converges. So here's the kind of the frustrating thing. You can see how we've built all these things. The only reason we did sequences was that so we could understand series. The only reason we did all those convergence tests is so that when we got to a power series, we can test its endpoints. And the only reason we did a power series was because eventually I could write functions as power series. So all those things built up to basically this moment, but especially what we'll do on Tuesday. And I'm going to give you what's next on Tuesday is, see, right now we're kind of just like doing this weird creativity of saying, like, if I've got a function and I want to write its power series, I somehow have to find some weird relationship to the one thing that I know. Well, some things don't relate to that at all. Like, what if I wanted a power series for sine x? Like, you don't relate it to 1 over 1 minus x. It's just, there's nothing that relates. Log x doesn't relate to this, right? A lot of things just don't. E to the x doesn't relate to this in any way. So instead of finding these weird connections, we're going to come up with a mechanical process that says, here are the steps. You start from any function, and you can get all the terms of the series for its power series and eventually write it in its appropriate notation. So that's what's coming next. Let me give you one more example. I'll have you guys try this.
So how would the calculator find the answer for x's that are in the region of convergence?
Well, there's actually pretty easy ways to do that. Typically, what you can essentially assume, more or less, is that from the center, which was 0, you can usually basically go to the first undefined point, right? So 1 is undefined in this function. So we can really go from 0 to 1, and you can go from 1 on both sides, essentially. They have some creative ways of figuring that out. That's a good question. A lot of the things that we will look at as like the main interesting functions, e to the x, e to the x, sine x, cosine x, etc., they're actually going to converge for all x's. So for a lot of the things, it doesn't even have to worry about it. Well, Nicole says, by the time this class ends, I won't ever need a calculator again. That's a true statement, but you will still want one. No one ever wants to do this by hand. All right, so find a power series for this. F of x equals log 1 minus x. So see if you can find a relationship between this and the one thing we know, and then go from there. The final answer should be this, by the way. Okay. Note that this negative sign is not in the parentheses. It's not being raised to anything. That's just a straight negative sign. All right, I'm putting the work up there so you can check it out. All right, so how's that looking? All the work is up there, so it's really a short problem, but there's that little trickiness of trying to relate the function to something that you know. Okay, so you said you get how the process works and how the relation works, but not the steps. So once you figure out that the derivative of something equals to this, right? You figure out some relationship of the function you want to the series that you know. It's really just solving, at that point, an equation, right? So it's no different, really, than if I said, I don't know, root 4 is equal to x or something like that. I don't know. Let's do that. 4 is equal to root x. And if I give you 4 equals root x, you'd have no problem solving it. You'd say, well, I'm trying to solve for x, and I've got a square root of it. So the only thing I could do is I would square both sides to get rid of the square root, right? Figure out the operation which undoes what's there. And I get x equals 16. So it's really not different here. You've got, forget this middle piece for a second. You've got the derivative of what you want is equal to this summation. So this is what I want. I want this thing. So how do I get rid of this? What's the inverse operation of the derivative? And the answer is the integral. So I have to integrate both sides. So what I'm really doing right now is the integral of the derivative of log of 1 minus x. But derivative of an integral, those cancel out, just like square of a square root. To get what I'm looking for standing alone, But of course, I had to integrate the other side as well, right? Doing the same thing to both sides. So that's the process of the steps. Once you can write the relationship, the rest is actually not too bad once you've done one or two and got comfortable with it. But if you find it confusing to you at first, like Kevin does, most people do. Most people find it pretty confusing at the first beginning. And is this going to be on the midterm? Well, by the midterm, you mean the third exam? I would say it could be, yeah. All right, so we got, 1 or 2 minutes here to just discuss the last thing, which is course evaluations are open. So I would appreciate if you guys all go on and fill out the course evaluations. I think you should have gotten an email. Or you can do them through, I guess, Canvas, right? I didn't actually see what platform they're using these days. Let me check the email. They're on Canvas. You can access the course evaluations at your Canvas and just do it for this class and I guess all your classes. And I'll just take a second to explain the importance of them, especially if you're new. But the school does take course evaluations very seriously, especially for adjuncts and lecturers and people who do not have tenure. That could very well mean the difference of them getting rehired for another year or not, getting let go. Even for people that do have tenure, though, if they start getting really bad evaluations, the department chair will take that very seriously. And they, maybe will lose some funding or they'll be asked to fix their performance and that sort of thing. And similarly, people that get very good evaluations, could be eligible for some school awards or that sort of thing, or generally just are looked upon highly by their department. So I think it is an important thing to give those feedback. I always like to read them. There's some comments that you can fill out. There's a bunch of ratings, 1 to 5, I think, of how good was the course, how good was the homework, this sort of stuff. So that's mainly what gets looked at by people that are trying to see who's a good and bad professor and making decisions. There's also things on the back, which is mainly for the individual professor to just see their own feedback. And that's just some general questions like, what did you like most about the course? Tell me a little about the professor. And I really do appreciate reading those things eventually when the time comes. You can leave an inside joke or something like that so I know who it is. But other than that, they are completely anonymous. So there's no way anyone can know who you are. You didn't used to be that way back in the day, but now it is. So you can fill them out. If you want to trash me, you can feel free to do that. Or want to get some professor fired. They're not going to know it's you. We don't get to read anything until after the exam, somewhere in the middle of the spring semester. So if the whole class gives someone a bad professor ratings, they're not going to be able to take it out on you in your final grades or anything like that. It will only be visible to them long after that's done. But like I said, I do like to read those comments. It's interesting to see if people leave some random thing. I'll tell you the weirdest comment I ever had on a course evaluation. It was an inside joke, but the department actually read them and was like, "What the heck does this mean?" So I just had to set the stage real quick. There was this guy, he's a super serious Indian guy, exceptionally smart. He got like hundreds on everything, sat in the front. And, he just was a machine. He just silent and got everything right. And there's another guy similar next to him, and they were also very well made. And this one day, I was, doing my lecture, and all of a sudden I hear a commotion from that table. And that's very unexpected. So I just kind of let it go on for a little bit. And I just continued to hear them like talking to each other. And I just had to turn. I was like, is that, what's going on over there? And the guy is like this. And he's like, I've got a bloody nose. And you can see there's blood in his hands. And I'm like, oh my goodness, are you all right over there? And he's like, oh, no. It's fine. I bleed about once a month. I was like, oh. And the whole class, of course, just starts laughing. So that's what he wrote on his course evaluation. He's like, sorry for my monthly bleeding. And then the department was like, what relationship do you have to this person? I was like, oh, this is a long story. But so, avoid that sort of comment, I guess. But anything else is fair game. So, if you can fill those out, I think you have like a week to do it. But, maybe you could just sign on now and do it. It probably shouldn't take more than 5 minutes. Otherwise, we are good to go, and I hope you guys have a nice weekend.
Have a nice day, Professor.
You too.
Thank you.